Okay, in this video we will solve an example on induction motor. So here we have a 380 volts line-to-line 3-phase 4-pole Y-connected induction motor, and in the question the torque expression is given as a linear function of the slip, and actually in the previous video we already derived that expression. So R2 prime is given, and the motor the motor is used to drive a load at precisely constant speed of 1500 rpm. The load torque can be expressed as some constant load plus linearly increasing with rotor speed. So let me draw here the characteristics. So if this is speed, this is torque. TL has some initial value of 10 Newton meter, so then it increases linearly like that, something like that. Okay, so TL is equal 10 plus omega r. So actually if we draw that thing, so if this is, I think it's not given in the question, but it is driven by 50 hertz waveform. If it is something like that, say this is the synchronous speed, and if this is a 4-pole machine, okay, so the synchronous speed and synchronous for a 4-pole machine will be 1500 rpm. Okay, so the question asks, propose a method of speed control for this purpose, and our requirement is we want to drive that load, okay, precisely, I mean this is omega, but this is equal to like 1500 rpm, for example. Okay, so I want to run that machine exactly at that value, but it asks us to choose a speed control method. I mean, if just to remind you, so we can change the magnitude of voltage, connect some external rotor resistance, you know, we can play with those parameters, but both with the voltage variation at 50 Hz or external rotor variation, it's not possible to move. It's not possible to move that synchronous point. So I can change the torque. I can change the voltage or resistance, so I can move the rotor induction motor torque characteristics like that. But it will not be possible to run the motor precisely at 1500 rpm because I have to have some kind of sleep for that purpose. The only solution would be to use a variable frequency drive. Right here, frequency drive, short for VFD. So I can maybe play with the frequency. Okay, I can apply a larger frequency and I can get the intersection point. Okay, I can get the intersection point at that characteristics, and I can estimate, it's given in the question that I can estimate the torque expression linearly as a function of slip. So we can find the exact rotor speed and what should be the torque of that speed, so I can find the operating synchronous frequency. So actually that is what asked in the next step, like in part B, and let's start with that one. So at B, what is the slip of the motor, right? So let me get rid of myself. So I want to run the motor at 1500 rpm. Okay, I can calculate the rotor speed at that position. If this is revolutions per minute, this is frequency, revolutions per second, hertz, times 2p is actually 157 radian per second. And actually I can calculate the torque. Okay, I will I'm going to calculate the torque here, and it is radian per second plus 10 Newton meter, so it is 107 Newton meter. So at steady state, okay, at steady state, I should have electrical torque is equal to load torque, so that corresponds to that intersection point over here. So if I have that characteristics and I know the voltage, I know the R2 prime, they are all given, I can calculate the value of slip, right? So let's do that. So electrical torque, which should be equal to 167, is equal to 3 V1 square omega s times R2 prime times s. Okay, so let me put those things in place. 170 is equal to 3 times. So now the problem is, what should be the V1? Okay, what should be the V1? So if you think, yes, maybe you can give a constant voltage, but as you increase the frequency, then you will put the machine into a field weakening region. So that's why we want to apply a constant, okay, V by F ratio. So I want to increase the voltage linearly with frequency, but I don't know yet the frequency of the state, but I can actually calculate. So let me draw a table here. So I know the V1 at frequency. So I am applying 308 volts, but that is a line to line in a Y connected machine. So I need to divide it by square root 3. That is equal to 220 volts. Okay. So at what frequency? So at 50 hertz. So if I want to give some frequency, actually you can calculate the ratio. It is 220 divided by 50. So it will be 4.4 times of electrical frequency. Okay, if I increase the frequency, I should increase the voltage. If I reduce the frequency, I should reduce the voltage. And for, if I write everything in terms of omega s, okay, I write everything for omega s. So omega s is the actual mechanical, let me write here, mechanical synchronous speed. Okay, I'm not talking about the electrical because I will use it in the torque expression. So we already calculated it. This is the synchronous speed. Okay, I want to run my motor at, not exactly at that frequency, larger, higher frequency. So for that it was like 50 pi, but actually if you have a look at here, that is not my synchronous speed. That is the I want my rotor to operate at when the motor we apply 50 hertz, so the synchronous speed is that one, but due to slip it will be running at a lower speed. And similarly, if I want motor to run at like exactly at 1500 rpm, or this is 2 pi 157 radian per second, so the actual synchronous speed will be higher. But at the end, I can write a relation between that one and the other one. So at 220 volts, okay, my synchronous speed was 50 pi, mechanical synchronous speed. And if I increase it, okay, for omega s here, the voltage should be similarly with that one. It will be 220 divided by 50p times omega s. So I don't know the actual operation speed, but the relations of the voltage with respect to synchronous speed will be like that, as we have 50p to 220 volts ratio. Okay, so if I just put, okay, I don't know that value, I can, instead of V1, so now I can put that value, okay, 220 divided by 50p times omega s square instead of V1. Okay, I have omega s times R2 prime, and actually R2 prime is given as 1 in this question, so I can eliminate that one. So this is slip. So let me write everything here on the new page, so I know that one is equal to 220 divided by 50p, and that one cancels, so this is square times omega s times slip. So actually I have like two unknowns, but I can write the slip in terms of the rotor speed and omega speed, right? I already know that one. So what is that? So I know omega s synchronous speed minus rotor speed. Okay, this one is rotating at, I know it was exactly rotating at 1500 rpm. But don't forget these are radian per seconds. And if I divide that value by omega s, I can find the slip, right? Slip is equal to the difference between the rotor speed and the synchronous speed divided by omega s. Then I can put that value, okay, I can put that value here. So let me write that one again. 3 times 220 divided by 50p squared times omega s times omega s. Instead of slip, I am writing omega s minus omega, r divided by omega s. So that one cancels out, and I can calculate the omega r. Okay, let's do that. Or let me write that one. So omega s minus omega r, if you divide that value, and let me check my notes, to calculate that one, it is 28.4 radian per second. So I know what should be the exact difference. Okay, if you think this is in radian per seconds, I know what should be that distance over here. Okay, that has to be 28.4 radian per second. So I will have that required torque. Then I can find the required, okay, I can calculate the required force as like 28.4 radian per second. And what is omega r? I know it is rotating at 1500 rpm divided by 60 times 2p, and it's all in the mechanical system, plus 28.4 radians. Okay, and the synchronous mechanical speed, if you calculate that value, you will find as 185.5 radian per second. And actually you can divide that value by 2p, and you will find is like 59 hertz. Okay, 59 hertz is the applied frequency, and I know V1 is equal to, remember, I calculated it like that, so it will be 4.4 times Fe, okay, 4.4 times 59. This is the phase voltage, okay, and if you multiply that one by 4.4, it is around 260 volts, okay, and V line to line voltage is equal to 450 volts. So if I am applying, go back, if I am applying 380 volts at 50 hertz, in order to increase the speed just precisely at 1500 RPM, I need to apply 59 Hertz. And if this is constant V by F operation, I'm applying 59 Hertz. So 380 multiplied by 59 divided by 50, or that ratio is 4.4, and you can find 450 volts. And let's calculate the slip. Okay, that is what it was asked anyway. The omega S minus omega R divided by omega S. So it is 28.4. Okay, that difference divided by 185.5. So this is 0.153, which is a reasonable value. Okay, but don't make the mistake like I know the torque, I know the initial values, so I can just put it in place. Okay, that slip and that synchronous speed will be changing once you change the frequency, so you cannot use the 50 Hertz value. Okay, so in the V by F operation, that equation still holds, but you need to be careful about the value, exact value of the voltage and the applied frequency. Okay, so in the next section, it asks about give a rough estimate for the efficiency of the motor under these conditions. What should be the efficiency of the motor? Okay, let's have a look at that one. And it just gives a rough estimation. Okay, again, you know, we don't know much information, but let's try to plot the equivalent circuit. I have that one, R1, JX1, JX2 prime, R2 prime, okay, and 1 minus S over S times R2 prime. So I know the value of S. S is 0.153. R1 probably is not given, or it can be neglected. Okay, so you have that component, which is the rotor heat loss. That one is actually responsible for mechanical power. Okay, so again, it is really rough and you need to know R1, but what you can do is within those information, I can write the output power as I2 gain 3 for the sake of completeness, but it doesn't really matter. In this case, 3I square 1 minus S over S times R2 prime. This is the mechanical power, divided by 3I square 1 minus S over S R2 prime plus R2 prime. This is the kind of input power. Okay, so you can get rid of all those things. In the top you have 1 over S divided by S R2 prime, and here if you add that one, S goes here, so it becomes R2 prime over S. Okay, so it cancels with that one, so you find it is 1 minus S. Okay, efficiency can be approximated as 1 minus S. So as the slip gets smaller, your losses in your system get smaller, so your system gets more efficient. As the slip gets larger, again the efficiency drops. But again, that is using just that approximation, and we don't know the value of R1, so probably it is less than that value. But just to give you an approximation, if you have that kind of value, efficiency is 1 minus 0.153, so it is less than this, around 84.7%. So with the addition of friction and with the addition of R1, maybe the parallel branch, in a practical case, the efficiency will be lower. But again, I think it just shows you the relation between the rotor heat loss and rotor mechanical loss. So at least what you can say is, as the slips gets bigger, the efficiency drops. Okay, so it's proportional with 1 minus s. So in the next part, what is the minimum value of the starting torque the motor must produce? What is the minimum value of the starting torque? So it is that value I need to give, that amount of torque. I need to produce a larger torque than that one, so I can start my machine. Okay, so I can calculate so TL is equal 10 plus omega R. So TL is equal 10 Newton meter at 0 RPM. Okay, so electrical torque will be larger than load torque, so electrical torque should be larger than 10 Newton meter if I want to start. Again, how quickly you want to start is a different story, but the question asks you, what should be the minimum value. So the minimum starting torque should be 10 Newton meters. Okay, thank you.